Let's start. And I want to do today is talk about the idea of emergent linguistic structure in deep contextual narrow representation. And at this point, I probably split the audience between people who are, oh, I know what this means, and people who I have the idea what this means. But I hope for the latter people will become a bit more evident. And in some sense, there is a mode setting of talking about something what's happening with the linguistic structure and natural language processing. And today we'll introduce the idea of language model and how we got from there the contextual representation. Then, in particular, to talk about the idea of transformer model and math model, which has been extremely influential in recent natural language processing. So the idea of language model is in a context we want to predict the probability of different words occurring. So if the context is the student open there are likely words to appear, like books, laptops, exam, and various words. So effectively, we want can do is put a probability distribution over what words will appear in a particular context. And so this is very simple notion of a probability model over words has been incredibly influential in all areas, like natural language processing, like speech recognition. But how do you build a language model? Okay, in the dark ages, approximately 2002 2003, shall we say the people built language model was you have got a lot of text and you counted up how often different sequence of words occur, and you could get conditional probabilities by dividing how many times the word this is in the sequence the student open their books. Compare how often the sequence the student open the occur. But this is a classic example of codes of dimensionality. Yes, because if there are zillions of different words, and if you can there is a zillions of parameter, you can possibly find enough text to estimate long context. And some easier are made assumption, like a Markov's assumption. And here a couple of words of context are enough. And and we are ready to introduce this question. And how this model relate to linguistic theory, the structure of language that people will think about in linguistic. And the answer about 30 years, passionately argued by linguistic, has been, this model just in a way capture the intricate, rich structure of human languages. And they know a little bit about it. And they capture the fact that you tend to get a word sequence like prepositional article, noun article, adjective noun, but in any case don't have any abstraction. They don't capture concepts like part of speech, like a noun, verb, not even the grammar and the structure of human language. And I guess really the answer for trying to capture the structure of human language is that we have built explicit models that try to put the latent structure of sentences. And since about 99, main way in which that is been done is that human then annotate long part of linguistic text with a structure, such as latent structure, such as part of speech, such as grammatical structure. And so people have spent several decades annotating large amount of human language text with this kind of information, like in this example, reference or part of speech. Then build model, machine learning model, to recover this kind of structure. And in some sense, that's unique of what has been to the dominant position in linguistics, that since 1950s, most prominent exposed by Norman Chomsky. Yeah, because Noam Chomsky has argued that the amount of evidence that human children get is too limited, too noisy, too unclear that human children possibly work out the intricate structure of human languages. And just from the input that they receive, that is actually part of human genetic endowment, that there are language-specific endowment in the brain that lets humans to understand language. And kids decode human language very quickly. In the first period, they can say 1 or 2 words. Then there is a period where children realize there is an underlying recursive system. And later, so what's happened more recently with language model, about in 2010, we can represent the word by a vector real numbers. And so once we have that, we had a sort of solution to the codes of dimensionality, because this vector can represent in multidimensional way the similarities between different words. And our model can exploit that to do a better job at prediction, and that was the initial work of Joshua Bengio. And so that give a way of avoiding the codes of dimensionality. But for long context, later, recurrent neural network maintain a state through time and give us some expectation of doing long distance prediction. And so we start with words the stupid open their we have an embedding for this word, which we learn. We then feed that through recurrent neural network, which builds up a state at each time, and which maintain a representation of the history and base it on that recurrent state. And we then predict the probability of different words occurring as the next word. And for about the decade or so, that's the way things have been. But around 2017, people focused on observation of what were they doing. Here we had the opportunity to extract a lot more power in representing, working with language, because we can take this hidden state, okay, and saying it's a hidden state of recurrent neural network, but we could say this is a meaning for the word student appearing in a particular context, okay? This is a meaning for the student appearing in a particular context. And okay, so for understanding the meaning of word that people have in recent 50 years, I've built models of word meaning by looking at the words that arise in the context of word. But the standard way of doing that is that you can learn one meaning for a word type without a particular words. For example, banking. Okay, what do you do is collect up of contexts of banking and then analyze them and say, okay, I have generated a meaning for banking which might be a word vector. But sometimes, okay, the meaning are different in different contexts. And there are many kinds of meaning, and traditionally people have worked with notion of splitting word into word sensing. Like in this example, the word broke of different contexts of use. Okay, and we say what? What? What we really have is we have a meaning of a word in context, and we should be able to compute that with the help of the context. And so the people have said, well, let's take this idea of deep contextual word representation and taking those hidden states of neural network and just scale it up to really big neural network. And there have been succession of work where effectively people are building even a very big neural network to generate this deep contextual word representation. And what people have found in that is that as the representation, your amount of training data gets bigger and bigger, there is just a huge improvement how well this model works. So part of this is just scaling and making things bigger and bigger. So the other part is they use a new type of neural network called Trasformer neural network. And we say, okay, there are recurrent neural network. They maintain these hidden real vector states that capture some of the past. That means everything we know about the past has to be sort or cramped into this one vector. And later say, well, maybe we should use the hidden key mainly as kind of a key, like a hash key. That will let us look back in the past to see which part of the past are most relevant. Okay, and so the way that's is done is you are calculating some kind of similarity score. Sorry. of similarity score between your hidden state and past hidden state based on that you're putting. Okay, sorry. Uh, okay, sorry. Google come up a radical idea, and we are making so much use of attention. Okay, maybe we could just build model that's all about attention, forgetting recurrent neural network. That's actually enormous computation advantages because recurrent neural network have been really friendly to the GPUs. And in 2007, Ashish Bashbani at Google, in paper Attention is All You Need, proposed a new important idea. And we are making so much use of attention, maybe we could just build model that's all about attention. And that actually enormous computation advantages because recurrent neural networks has been really friendly to the parallel computation of the GPUs. And with GPUs we can do everything in parallel. And the recurrent model isn't parallelizable to the same degree. Well, the idea was that we could start a very deep model, okay? And again, people think, and if we make very deep model with sequence of layer of attention, then that will arise us to do a series of lateral information transfer in depth rather than horizontal sequence. And simply, so this was the idea of Trasformer model. And okay, let's start. So the basic idea is that they are going to use attention everywhere to calculate things. And let's start with simple things, where the attention is just a dot product between two things. And Q, query, key, and V are both vector of sentencing input. And they do more complicated version of dot product between two things. And so you are calculating the similarity as a just dot product between query and key. And then, based on that, you are going to be using the vector for corresponding value. And if we have multiple queries, okay, multiple Q, we stack them into matrix, and this equation becomes this, okay, and okay, so equation here, what we are calculating is where you are looking uses the softmax over query, okay, and so that's basic attention model, and so that at saying it way adds a little bit of complexity. So there are a couple of other things that they do. The first is that okay, when the dimension gets so large, so that they sort of do a some normalization by the side of hidden state dimension. And okay, the second idea is well, attention is great, but maybe it's bad if you only have just one attention distribution, because you are gonna only attend two things one way. Okay, so they introduce this idea of multi-head distribution. And so you are going with multi-head attention is you have your hidden state in your system and you map them via projection layer, which are just multiplication of different W matrix as a linear projection in sort of different lower dimensional space. And then you use each does calculate the product attention, and so you can attend to different things at the same time. And okay, now I show you an example taken from the presentation of the paper Attention is All You Need. And given a simple input sentence, okay, action get results, and we represent the words by a vector to better understand what has happened. And for each input vector, we have query vector, key vector, and value vector. This vector is 64-dimension vector. And self-attention calculation for each input vector to calculate the vector of action vector score, we have to compare it with the second vector and third vector. The score of first vector is calculated by doing a dot product of query vector and other vector, and then is normalized by the square of the root of vector size key. Okay, size is 64, and the square is 8. Okay, and then results are added together. Okay, results are added together, and we obtain a self-attention vector for the first word, the word action. Okay, this is due for all input words like gets, like results, and okay, the final step is concatenate this value. Okay, and self-attention is calculated several times, both in parallel and not, and the output are concatenated and transformed linearly. And this is a summary image of multi-head attention. Okay, perfect. And the most famous at the moment attention model has been used in NLP is built bidirectional encoder representation from transformers. And so the idea of it is that we are going pre-train AI transformers by doing word prediction with it, and then that will give as a kind of general understanding of human language ability, which will then be able to use in different particular tasks. And so the way this model has been trained is that you are taking the sentence, the man went to the store, buy a gallon of milk, and you blanking out some words, and you wanted to train a transformer model to predict these blanked words. So it's going to use attention to context to try and predict the words. So this is then solved a self-attention in math sequence model. So we are doing the same kind of attention computation of calculating attention score in context to get an attention distribution and attention output. And we're restoring everything that happened beforehand. And all you need to know is that miss one word. But as we adopt the transformer stack, we start to get more information. And the second innovation, say, like transformer, say, well, the basic model just had one similarity calculation have two similar things. And then where one sort of waiting to pay off, to pay attention. But if we wanting to generate, there are probably sort of lot of relevant words in context. And they are relevant in a lot of different ways and for a lot of different reasons. But okay, wait a moment. Let's take a step back. And for those who haven't understand it, what is the relationship between transformer and BERT? So essentially, it's using the encoder from transformer block. Okay, BERT using encoder from transformer block. And so there is actually an interesting new idea that these people had. And the idea was standard language model are unidirectional. Okay, standard language model are unidirectional. And that's useful because it gives you a probability distribution of a language model. But it's bad because you'd like to be able to do prediction from both sides and to understand the meaning and context. And there is a second choice, which is you can do a bidirectional model when you incorporate information in both ways. And so, for example, if you run bidirectional LSTM and then you merge the representation by concatenation and then feed them into the next layer, okay, when you're running the next layer, the forward LSTM, okay, forward LSTM will have already gotten information about the future from the first layer. And so it ends with the words that have already seen in the future. So you have this sort of non-complex generative model. But in BERT, they want to do things a bit differently. So they can have bidirectional context without both being able to see themselves. And the idea that they had is, well, we're gonna train things with a transformers encoder. But we're gonna do is mask out some of the words in sentence, okay? And the sort of language model, like goal, which will not be a true language model. That's a sort of generating probability of sentence, which is standardly done by working left to right, but it will have the goal of filling in the blanks. So you see this context, like a 3 or 4 slides ago. The man went to the mask to buy a mask of milk, and what's your training goal is to say try and predict what this word is which you can do with a cross-central pillars to the extent that you don't guess store. And you are training a model to fill these blanks, okay? And the rate at which they blanks word is essentially one word in 7. And because if you blank too few words, it gets very expensive to train. And if you blanks many words, well, you have blanked out most of the context of a word, and that means it's not very useful to training. And so the expectation is using inside Trasformer model, and this trick of blanking out words and predicting it using a full context will ask them to use two-sided context and be much more effective. And in addition, they think it will be useful have a second goal where you predicting relationship between sentences. Okay, predicting relationship between sentences. So they secondly have a last function, which is let's up to sentence, where the sentence might be two successive sentences in the text, or a sentence followed by a random sentence somewhere else. And we want to train the system to predict when you have C a correct next sentence versus random sentence. And so you're also training a last based on this next sentence prediction task. Okay. And so what the end looks like this. They have from the input they'll have a pair of sentences. My dog is cute. Sep, separator, token of separation. He likes playing. Okay, the words are represented as a word piece. There is a token embedding for each word piece. Then there are positional embedding for each word piece, which gonna be summed with the token embedding. Finally, there is a segment embedding for each word piece, which is simply whether it comes from the first sentence or the second sentence, before or after the separator. And so you are summing those three things together to get token representation. Okay, and then you're going to use those in Trasformer model, where we have losses to the extent that you can predict the masked words. And it's a transformer like Trasformer before. it's trained, but it's trained on the Wikipedia. Okay, and then build two models, BERT base or BERT large. BERT base have 12 layer, okay, 12 layer of the, this is a transformer block, 12 layer encoder and 12 of decoder. 24 layer of encoder, 24 layer of decoder. And okay, transformer block 1, 2, 3, 12. Okay, so then what they wanted to say was this a pre-trained model, okay, evaluated on these losses and masked language model and next sentence prediction. And we could take this model, okay, we could take this model pre-trained and it will be incredibly useful for various different tasks. We could use it for name entity recognition, question answering, natural language inference, task sentiment analysis. What we're going to say is just keep on using this and keep on using this transformer network that we trained as a sort of language model, but fine-tune, okay, fine-tune in a particular task. And what we are going to change is we are going to remove top level prediction. We remove top level prediction and the bits that predict mass language model and accent and prediction, and we are going to substitute on it on top a final prediction layer that's appropriate for the task. Okay, as we see in the slide before, the way BERT represents both vector give us the ability to extract latent information. And for example, the token embeddings, segment embeddings, contain semantic information and syntactic information. But how much syntax information is embedded in this universal sentence encoder? Universal sentence encoder transforms like models. For example, BERT. Okay, we found the answer in this work that claim that BERT captures linguistic information in this way. Semantic feature in either layer, syntactic feature in middle layer, and surface feature in lower layer. Okay, but what is mean by layer? Simply, as said before, when we have to solve a classification task, we input the sentence to the model, and but encoder returns the input encoded in vector, okay, and the researcher, the developer, can choose to train 1, 2, 3, 4, if you 1 layer, 2 layer, 3 layer, and can choose to train until 10 or 12 layer. And these people claims that taking, for example, taking Bert Bayes, Bert Bayes capture linguistic information in this way. Semantic feature in the 10th and 11th layer. Syntactic feature in 8th layer. And subphase feature in the 1st, 2nd, and 3rd layer. And but in 19% on cases, BERT is used in following way. No layer is trained, or the first or only the second layer is trained, and the vector representation of the input coming out of the last layer is taken. This is to reduce the usage of GPUs and maintain a good performance. But in some cases it's not enough. And many times syntactical information is mitigated and not considered. And okay, so we decided to understand what's happened if we concatenate BERT with a purely symbolic representation. And the symbolic and syntactic representation for excellence are parts 3. Okay, parts 3. And this is where Kermit was born. Okay, we come back to the concatenation between these vectors. This vector that represent parts 3, okay, syntactic representation, and the vector that is the output of BERT encoder. And okay, in the we use Kermit for represent the syntactic information, and the syntactic information is embedded into one vector of 4,000 dimension, concatenated with that BERT vector. And the BERT vector have 7, 6, 8 dimension BERT base. And this combination allows us to obtain better results in cases where the syntax influence more in the final classification. And yeah, in this work there is not only concatenation part of BERT vector with syntax vector, but for a reason of time I won't be able to tell you, but I won't be long now. But I want to show is simply how we can use BERT encoder along with other things. And okay, as we've seen in this graph, on the axis is the layer trained, okay, of BERT, and this is the accuracy. Okay, we can observe that at the increase as training layer increase, okay, of birth base, line, blue line, the accuracy increase. Almost always this is this phenomenon, and we can say other line. We can see other line that there is a simple concatenation with the vector of Kermit and the vector of Bert, and this concatenation then feed into shallow neural network, and are three lines because a different shallow neural network with different layer, different numbers of layer. But we can see that this concatenation many times increase the performances, like in this example, and sorry, this is three classic well-known task of sentiment analysis. And okay, so in conclusion, we can say that absolutely BERT is changing the world, but all the past is not through any way, and very often it can help us to get more from this new powerful model. And okay, thank you for the attention. I think that tomorrow I think I send you slide and PDF and
Okay, thank you for this, and I'll upload them, guys, on Moodle as usual. Okay, I don't know. I repeat.